Hello everyone, my name is Roland Martinez,
And my name is Tolentino.
and today we are going to show you our presentation for the activity 8, which is quadrature phase shift keying in ECE 122L section E02. So what is QPSK or quadrature phase shift keying? It is a form of PSK in which two bits are modulated at once, selecting one of four possible carrier phase shifts from 0, 90, 180, or 270 degrees. Its application is commonly used in satellite transmission of MP2 video, cable modems, video conferencing, cellular phone systems, and other forms of digital communications over an RF carrier. So QPSK is a variation of PSK that uses a DSBSC or double sideband suppressed carrier modulation scheme, which sends 2 bits of digital information at time, called the bigits or binary digits. Instead of the conversion of digital bits into a series of digital stream, it converts them into a bit pairs. This decreases the data bit rate to half, which allows space for the other users. So what you can see on the screen is the QPSK modulator block diagram. The QPSK modulator uses a bit splitter, 2 multipliers with local oscillator, then a 2-bit serial to parallel converter, and a summer circuit. And that modulator inputs the message signal, signals even bits, which is for example is second bit, fourth bit, sixth bit, etc., and odd bits, such as first bit, third bit, fifth bit, and so on, are separated by the bit splitter. Then and are multiplied with the same carrier to generate odd PSK. So you can see there are 2 PSK I and PSK Q. And the PSK I are for the odd, then for PSK Q are for the even. Then the signal is now phase shifted by 90 degrees before being modulated. So what you can see is the plot of the QPSK waveform. So the QPSK waveform for 2 bits input is as follows, which shows the modulated result for the different stances of binary inputs. So this is the carrier channel or sinusoidal waveform. Then the modulated result is a QPSK, which is similar to PSK but with a bigits or binary digits. So next is the procedure for the activity, which we need to create a Simulink model for a QPSK modulator on a new blank model in the MATLAB Simulink. Then showing all the block names and formatting them into block name which is always set to on. Then we need to rename the blocks for the corresponding function names, like 0 degree, 180 degrees, 90 degrees, and negative 90 degrees for the initial inputs. Then the most significant bit MSB and the least significant bit LSB. Then the switches for the PSK inputs. Then the summer or this sum, which is multiplex using the reference with the reference sinusoidal wave, and the output is monitored using the scope. Then we need to set the stop time for the simulation for 1 second and run the simulation. Then we need to observe the output on the scope and copy the figures and answer the tables that is asked in the manual. So before we proceed with the interpretation of results and conclusion, we are going to show you our time-lapse video for the design of the block diagrams for the QPSK, and showing the output results. Hello everyone, my name is Martinez, and this is a video demonstration of the activity 7 in ECE 122 section E02. And the activity is to simulate the block diagram of the quadrature phase shift keying, or the QPSK. So let's proceed to the Simulink to simulate the block diagram. Then this is the output of the QPSK block diagram. So to zoom in on the signal for each time segment, I need to measure the phase difference and tabulate the answers on the table. Then copy the figure for each time segment by Ctrl C and paste it inside the designated box. So for 0.1 seconds, from 0 to 0.1 seconds, hoop, hoop, hoop. So this is the phase shift and the phase difference between the QPSK. So the phase difference is compared with the reference sine wave by the QPSK output signal. So to measure that, we can use the cursor for the measurement of the phase difference.
Good day, everyone. My name is Tolentino, and I will be discussing about activity 8, which is about the quadrature phase shift keying, or QPSK. So, binary phase shift keying, or BPSK, is a type of digital modulation wherein a single bit is represented by an equivalent phase shift to the carrier signal. The constellation diagram of a BPSK contains only two symbols, 1 or 0. In effect, BPSK can only transmit 1 bit per symbol. To increase bit rate without increasing the carrier frequency, the number of symbols on the constellation diagram can be doubled. Quadrature phase shift keying, or QPSK, is a process wherein each symbol is represented by 2-bit binary number, 2 bits per symbol, resulting into a 4-symbol constellation diagram. So in this figure, as you can see, the input, which is binary symbol, then in the output, it becomes an analog signal. So one possible QPSK scheme can be described by the constellation diagram and table shown below. Each phase-shifted signal represents 2-bit number, or 1 per symbol. The phase difference between signals can be illustrated by, by time plots shown on the next page. The phase-shifted signals are the solid blue sinusoids, and the original signals are the dashed black sinusoids. So next is I'm going to demonstrate and create the simulate model for a QPSK modulator on MATLAB. So this is the output for the multiplex of the reference signal and the QPSK signal. So that is all for my demonstration. Thank you. So proceeding with the interpretation of results, as we can see in the figure is the graph or when we double click on scope. So this is the output of the QPSK modulator. So this graph shows both the QPSK and the reference sine wave signal. So observing the result, we can see that the essence of using the multiplexer, because without the multiplexer, we will not be able to observe both the signals in a single graph, and without that, we cannot compare the phase difference of the QPSK signal to the reference sine wave signal. So as we can see, although it is not zoomed in, we can see that the reference sine wave signal is not in phase with the QPSK signal. So next, moving on, we also observed that there is a pattern in the 2-bit code, which is 110110 and 00. So this can be attributed to the different periods set in the pulse generators. So initially, both pulse generators would have an output of 1, which is why the first 2-bit code is 11. However, since the period of the most significant bit or MSB generator is set to zero point 0.2 only, while the least significant bit or LSB generator is set to zero point 0.4. And also the pulse width of both generators are set to 50%. It means that for both generators, their signal would change for every half of the period, in which for the MSB, it would change in every zero point 0.1 second, while for LSB, it would change for every zero point 0.2 seconds. So this is why we can see in this figure that after zero point 0.1 seconds, the MSB has gone back to 0, while LSB is still at 1, which is why the second 2-bit code is 01. So next is at zero point 0.2 seconds. So it is just the time that the LSB will be back to 0, since its period is set to zero point 0.4. While at the same time, the MSB has already finished its first cycle and is now starting its second cycle by rising to 1, which is why the third 2-bit code is 10, and as we can see, the graph displays the result. So lastly, is at zero point 0.3 seconds, where the MSB has already finished its half cycle again, which is why it comes back to 0, while the LSB is still not yet finished on its first cycle, which is why it is still at 0. Therefore, the last 2-bit code of the pattern is 00. And for the last pattern at zero point 0.4, the LSB has already finished its first cycle, which is why it rises to 1 for its second cycle. While MSB is again starting another cycle, which is why the 2-bit code comes back to 1, and the pattern continues on from the following values 0.5, 0.6 up to 1. So concluding this activity, quadrature phase shift keying or QPSK is a process wherein each symbol is represented by 2-bit binary number or 2 bits per symbol, resulting into a 4-symbol constellation diagram. Then the band efficiency of QPSK is twice that of the BPSK because 2 bits are transmitted in a single modulation code. Then, in a quaternary digital modulation, the quadrature phase shifting signal is generated when the phase of the sinusoidal carrier varies discretely with the quaternary digital baseband signal. Then, the phase of the carrier varies with the modulation signals 00, 01, 10, and 11. So usually with 1 and 2, we got two representing the two phases, wherein the first part is the 0 degrees, the 90 degrees, the 180 degrees, and 270 degrees. And the second part is the 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And that concludes our activity. Thank
Thank
you.
you.